What's up, y'all? How y'all doing? You've been seeing me doing some high voltage experiments, and I wonder if I will tell you a bit about what high voltage itself really is. Well, guys, I hope you enjoyed this video. Don't forget to share, subscribe, and comment anything you like about this video. In short, so yeah, I made many experiments, just like using ZVS circuits, using a transistor, or or even making a mux generator. Well, all of them involves a high voltage source. But what do you mean by high voltage? Let me show you. Let me break it down. Now, this is the traditional circuit that we all are familiar with since we are children. Now, what we see right here, this is a battery, this is a lamp, and this is switch. Now, when we close this switch, when this becomes closed, electrons starts to run through this electric circuit. For example, this will be the current flowing through the lamp. Just like this. We call it current. Current here, current which is represented by I. And the lamp starts to produce light. But this new concept that I'm going to show you is relatively higher. Now, what we use, the type of voltage that we are using is called low voltage, represented by LV. We say high voltage because this kind of voltage does not produce a shock on human body, which is about 67 volts, which is the limit. Now, this produces about, for example, let's say the battery is about 3.7 volts. 3.7 volts. 3.7 volts. But if we apply a high voltage instead of this small battery of low voltage, and we use it like a transformer of a high voltage, then we're gonna see something different. Okay, now, as you can see here, here's a transformer connected to a AC power supply, and this is the secondary coil is connected to, this one is a neon lamp. Neon lamp, you may know it all. Neon lamp, a small lamp, depending on where you see it. A neon lamp connected in closed circuit. Now, if we turn this transformer on, we'll expect this neon lamp to glow. But if we try to open the circuit, just like a switch, if we create a gap just like this, depending on the voltage that this transformer puts out, if it's high enough, for example, like a 90,000 or 100,000, the moment you cut off or you try to, disconnect this circuit, a huge arc will close the circuit, creating a spark through this gap. If you lead with a traditional concept of electricity, you may say this thing is open circuit, but it isn't. It's closed, regardless of its continuity. Still, this won't change anything. But what is the reason behind this electrons or currents jump through a gap? Well, that's because due to the potential difference. Okay, guys, now I've connected this was an iron lamp, and this is the service circuit and a flyback transformer. Thus, that creates me a huge amount of voltage. Approximately around, let's just randomly say 60,000. 60,000 volt is connected right here. Now, let's turn it on and see it. This neon lamp, and hopefully to turn it off. But as you can see here, it is open, but the LED is creating light. And this is a high voltage. See? Even if we separate the circuits, we say it is still a closed circuit. When we separate two, we call these two electrodes. Electrodes are such things, and they are metals that separated or suspended in air. Now, what will happen when we connect a 100,000 volt and we bring these two much closer? Now, when you bring the two close enough, they start to produce something we call corona discharge. Most of the time it happens on the sharp edges of the electrode. Remember that. When we start to bring these two together, we see something starts to appear, just like this. On the sharp edges, just like this. We call this thing corona discharge. What corona is, corona are small suspended and electrons at high speed trying to jump from one to another. Which means if this, for example, is okay, let's just this we call a corona discharge. Now, when the more we bring it too close together, something starts to happen. Electrons will slowly, these two will slowly come together. Will slowly come together, and the more and more and more we bring, these two start to connect. And then, boom, they are connected now. We call this thing, well, still we call it a corona, but now it's called an arcing. Okay, now let me show you by what I mean by a corona discharge and a frequency, and frequency that I tried to tell you. Now let's turn it on and let me show you. You see those glows on the tips? We call them coronas or corona discharge. The electrons are trying to escape or to jump through the electrodes. We see a tiny glow. Now when we bring them together, you see? Now the circuit is almost closed. And then, boom. Yeah, now the two of them are connected and we call it arc, or arcing. Now, when this happens, well, depending on the voltage type, and what I mean by that is this high voltage we are giving to the system, is it AC or DC? Because that hugely depends. If it is AC, the electrons at very high speed, very super fast. It's like in hundreds of thousands of meters per second. Just like a half or quarter or even less, 1/10 of a speed of light. So these electrons, we call them electrons, the subatomic particles, will fly out to the electrodes at extraordinary speed. Okay, once I said this, there are two more factors. As I said earlier, there are two types of voltage depending on the frequency. There's a DC and AC, direct current and alternating current. And also the second factor is frequency itself, because that hugely matters. Let's just say the current is a DC current. Electrons will travel to the negative and to the positive, depending on the voltage types and depending on the separation distance. Now, while that happens, DC is unidirectional. It only has the one direction, from negative to positive. But if we take like AC, let me change it right here. Let's just say this is AC. If this is AC, it must have a frequency. It's necessary. And also, it changes terminals depending on the cycle. Well, we both know that AC alternate its terminals depending on the time cycle, which means first it was positive, then it was negative, then positive, then negative, then positive, then negative. So these two changes alternatively. So this become plus and this is minus. Then when this happens, electron will travel this direction. And then when this cycle ends, the charges again switch places, which means this is minus and this is plus. So electrons go through this direction. Then this. Depending on the frequency, it will switch one to the other very, very quickly. Now, the other or the third concept is frequency. Now, we all know frequency is the time required for a vibration. Frequency is the measurement of vibrations. Now, what do you mean by vibration? Now, when we apply this voltage, in my language, I call frequency as how many times will you apply this voltage in how many seconds. So let's just say frequency is measured by hertz, which means 1 vibration per second or 1 cycle per second. So let's just say this voltage is around 1 hertz. Let's just say this is at 1 hertz. If this is at 1 hertz, there would be a spark. We generated a spark. So it doesn't matter which is like AC or DC. It doesn't matter now. Now let's just forget about AC and DC. So when 1 hertz happens, we see a spark just like this. We'll see just like this. The reason that it gives off this shape is that's, or well, in plural, those electrons try to find the shortest path or the easiest path. More preferably the easiest path, because this medium is air and air has many particles, so the electrons try to find an easier way to get to the electrode. That's why it has a wiggling. So 1 hertz will be like this. But things start to change when we increase the frequency. How many times will we apply this circuit, this voltage to the circuit? So let's just say this will change, for example, 100. Let's just say this is 100 hertz. 100 hertz. So that means that this spark happens 100 times in a second. When that happens, it gets slightly weird. This spark will start to be linear. All this. So if we apply 100 hertz to the system, the spark, instead of a wiggling or zigzag path, it starts to have more linear or more straighter, as I call it, more straighter arc. This happens because this spark happens so fast, even the air medium won't be a challenge at that frequency. So let's just say our final frequency be, for example, 1 megahertz. 1 megahertz, which is about a million hertz, million times per second. Even that is too high for air to be an obstacle. So this current or this high voltage, instead of being a spark, it slowly becomes a very linear. It will give a very linear an arc, a very linear and very straight arc. It will give just like this.
Apparently, my flyback transformer is DC with a frequency of 20,000 hertz. Now, as you can see right here, it's vibrating at that specific frequency, and you don't see much of a zigzag shaped spark. It's more like an arc with a more linear path, and that's all due to the frequency of it. If I lower the frequency, it will appear just like a spark, like we see around electrostatic objects such as Van de Graaff or any other electrostatic machines.
Moving on, well, I told you about the frequency, the AC and DC, and this will be the other thing that you will notice while creating this high voltage. Now, when you do this, let's just say I lowered the frequency a bit, about 20,000 hertz. When we do this, now, as we said, electrons at high speed beats the shit out of air. Well, that's what I can say about it. So the air gets beaten like 20,000 times per second. That is so high. So when we beat air like that at high speed and using electrons, the air itself will start to produce some kind of electromagnetic wave. The air starts to appear a bit purple, or what I mean is this arc will start to look like a purple line, just purple, just like you have seen in my videos or even other people's videos. It starts to appear purple. The molecules in air starts to be excited due to the set frequency at high speed. When you see in the band of spectrums or in electromagnetic spectrum, especially visible light, you find purple or violet at the end, nearly at the end of the band, relatively has higher energy than any of the rest of colors. So this purple is high energy. That's what it's trying to show you. But there's another thing. Purple is not the only thing that gets generated. Purple spectrum isn't the only thing that's getting produced, because electrons is hitting the shit out of an anode. So that kind of heat, that kind of kinetic energy and collision between these two entities will create heat on the anode, only on at the anode, not the cathode, because there's nothing colliding with it. It's escaping but hitting the anode. But in the case of AC, it's both. In the case of AC, well, as I said earlier, electron both hits the electrodes, so and hitting right back. So both will be created. Heat will be created on both sides or both electrodes. That will happen if we use an AC high voltage. But we're not finished here yet. There's another thing. Well, we said there's a purple spectrum and heat, which we call an IR or infrared. You may know it as infrared. And also the other spectrum that we cannot see is UV light. Ultraviolet is being created in this spectrum.
Well, just like I said, the color appears to be violet or purple, and there's some amount of heat on the anode of the flyback transformer. It's kind of warming up, but not on the other side, which indicates that this is a DC flyback transformer. And the UV is apparently invisible, but we can see it by the reflection of a white object, such as a paper.
Now, the last concept will be about pressure. Now, we all know pressure is the force per unit area, but we're not talking about that kind of pressure. We're talking about the atmospheric pressure. Now, for example, let's just say this is in a container. This is a container, and if we increase the pressure inside this container where these electrodes are placed, the arc starts to appear, the color, its spectrum starts to appear white. It becomes white. When we increase its pressure, it becomes a bit of white. This is white. If we increase the pressure. Now, when that's done, and also it becomes difficult for the electrons to jump through this container because the pressure, condenses the particles together, and which means, it increases this obstacle. If we decrease the pressure inside this container, it starts to glow, again, purple. But I'm not talking about this, it's a beautiful glow inside this, when it becomes vacuum. It glows beautifully. It's purple. Okay guys, now I will talk about the pressure concept. This is a syringe, and this is a bulb, a broken bulb actually, and connected to a syringe. Now I've connected this to the duct and increased the pressure. Okay guys, now let's connect this high voltage to a higher pressure. Oh, and by the way, I forgot. In order to check for how much separation distance is the voltage, according to the internet, it's about 30,000 volt per 1 centimeter. In which, for example, if it is 3 centimeter, if the spark is 3 centimeter, it becomes 90,000 volts, which is approximately just like mine. Just FYI. Now, let's connect this and let's see. And also, because we increase the pressure, the electrons, the high-speed electrons, tries to find the shortest or the easiest route, which is right about there. Right there. So it becomes more wider, and the gap that it escapes is really small. Now that, when we increase the pressure, now let's lose the pressure and create a partial vacuum and see what will happen. Okay, now you see it? It's silent. There's no noise, and you can see this. You can see it right here. When I connect it, one seems to be hotter than the other. It's creating heat on the other filament. And as I said earlier, there's not really a purpley gap between it, but we can see it on the edges. Now it's melting the filament, it's melting it. Now it's getting red hot. That means it is the anode. And the other one, the one with the corona, is a cathode. That means this system is partially vacuum. And who knows, maybe it's producing X-ray. Maybe I'm getting a cancer, God forbid. This is what it looks like when an arc is happening inside a partially vacuum or almost a vacuum space.